Welcome back to the wondrous emotional colonoscopy of organic chemistry. Today I'll begin teaching you about amino acids, peptides, and proteins. There are many slides required to cover this subject, but I promise that if you pay close attention, I will give you a shiny new monkey. Okay, that's a lie. But you will be much more likely to do better in class if you pay close attention, which might be more valuable to you than a shiny monkey. Only time will tell. To prevent myself from collapsing from fatigue, I've divided Chapter 23's lecture slides into two PowerPoint presentations. After studying the first half of this chapter that's covered in this set of PowerPoint slides, you should be able to do the following. First, define the following terms: dipeptide, tripeptide, oligopeptide, and polypeptide. Be familiar with the names, structures, and abbreviations of the 20 common amino acids. Now note, for this class you will not have to memorize them. Next, if given an amino acid's pKa values, draw its predominant form at a specified pH. Next, be able to calculate an amino acid's isoelectric point. And last, if given their pi values, that is, their isoelectric point values, identify individual amino acids' relative migrations during electrophoresis. So what are amino acids and proteins? Good question, my wondrous student who's now watching this over the internet and may or may not have actually asked that question. Simply put, amino acids are molecules that look like this one right here. They're called amino acids because they contain both an amine group right here and a carboxylic acid group over here. So we combine those two names into one magical word, amino acid. There are 20 most common amino acids found in all living things on Earth. I'll introduce you to these shortly. For now, suffice it to say that the only way in which each of these 20 amino acids differ from each other is the identity of this side chain R that's attached to our alpha carbon. We call these R groups side chains. Incidentally, you can draw amino acids in numerous different ways to indicate their stereochemical configuration. My favorite way is the way shown here. However, the author of our book prefers to draw them with the amine group pointing down like this. I want you to not freak out when you see it drawn one way or the other. They're both exactly the same molecule. The only difference is just that we've rotated around this bond right here to go from the structure on the left to the structure on the right. Amino acids generally bond together by having the amine from one amino acid condense onto the carboxylic acid group from another to form an amide bond like this one shown here. Now you can see that if I were to rotate around, let's say I think this bond right here, we could redraw this di-amino acid as looking like this. It's exactly the same. All I've done is rotated around here to poke this R group up and leave this R group here down. Now a chain or polymer of two amino acids bound together like the one I've shown here is called a dipeptide. A chain of 3 amino acids is called a tripeptide. A chain of 3 to 10 amino acids is called an oligopeptide. Of up to 50 amino acids is called a polypeptide. And a chain of more than 50 amino acids is called a protein. So in essence, all proteins are is just one or more large chains of amino acids bound together in a specific form. So just as a house can be assembled by binding numerous bricks together in a specified fashion, a protein is assembled by binding numerous specific amino acids together in a specified fashion. Amino acids are the building blocks of proteins. As I mentioned earlier, there are 20 amino acids that are the most common amino acids found in all living things on Earth. This table from your book, table 23.2, shows their structures, which I'm going to superficially introduce you to now. I want you to know, however, that I will not require you to memorize these structures in this class. That will have to wait for when I teach you guys biochemistry later on, for those of you who take that class from me. So here are the first 8 most common amino acids. Glycine, which has this structure here. And you'll notice that glycine's side chain is just a hydrogen. Alanine, which has this structure, its side chain is a methyl group. Valine, which has this structure, its side chain is an isopropyl group. Leucine, which has this structure over here, this is an isobutyl group. Isoleucine, which has this isomeric isobutyl group. Serine, which has this hydroxymethylene group. Threonine, which has this group. And cysteine, which has this group right here. Now, one important thing that I wish to point out here is that biochemists like to abbreviate amino acids' names to enable them to be written more quickly and conveniently. Thus, each amino acid has 2 different abbreviations. One is a 3-letter abbreviation, the other is a 1-letter abbreviation. Thus, glycine up here, for example, could be abbreviated as GLY if you were using the 3-letter abbreviation, or simply as G if you were using the 1-letter abbreviation. I should warn you, though, that not all of the 1-letter abbreviations are simply the first letter of the amino acid's name. That would be impossible, since some of them start with the same letter as each other. Hence, aspartate, which is shown right here, couldn't possibly have the letter A be its 1-letter abbreviation, because that is the same letter that alanine, another amino acid, uses. That's why we give aspartate this 1-letter abbreviation, letter D. Don't ask me why they picked D. So here are the next 9 of the most common amino acids. Methionine, whose side chain is this one right here. Aspartate, whose side chain looks like this. Now, I need to point out that aspartate is also known as aspartic acid. Those 2 terms are synonyms. So don't freak out if I say aspartic acid. Make sure that you don't get confused. Understand that aspartate and aspartic acid are the same thing. The next amino acid is glutamate. Glutamate also has another name, glutamic acid. Exactly the same thing. Asparagine, which has this side chain. Glutamine, which has this side chain. Lysine, which has this side chain. Arginine, which has this side chain. Phenylalanine, which has this side chain. Tyrosine, which has this side chain. You'll notice that tyrosine looks exactly like phenylalanine, except that it has a hydroxyl group in the para position of the benzene ring to the amino acid. And here are the last 3 amino acids of our 20 most common amino acids. Proline, which has this cyclic side chain. It's the only side chain in which the amine group of the amino acid is actually part of the side chain. Histidine, which has this side chain. And tryptophan, which has this side chain. Note that this heterocyclic aromatic ring right here is called an indole ring. You might remember that from one of our previous chapters. Tryptophan is the amino acid that has indole in it. I should mention here that 10 of these amino acids, which are shown with asterisks here, you'll notice that tryptophan is one and histidine is another, as well as 8 others shown in the previous 2 slides, are considered to be essential amino acids, meaning that we humans have to obtain them from the foods that we eat. This is because our bodies either can't synthesize them at all, or can't synthesize them in sufficient amounts for our survival. For example, we humans must eat phenylalanine because our bodies can't synthesize benzene rings. However, we don't need to eat tyrosine because our bodies do have the ability to put a hydroxyl group onto phenylalanine to thereby furnish tyrosine. Thus, if we're eating phenylalanine, our bodies have the ability to convert that into tyrosine. That's why phenylalanine is an essential amino acid and tyrosine is not. Interestingly, although we can synthesize arginine, which is shown right here, our bodies need more of it than we can make when we're in stages of our life that have lots of growth. Hence, arginine is considered an essential amino acid for children, but not for adults. Now, as we learned back in Chapter 22, amino acids can also be drawn as Fisher projections, just like simple carbohydrates. You might remember from Chapter 22 that simple carbohydrates in nature all have the D configuration, that is, the configuration where the OH is pointing to the right in the Fisher projection. Oddly enough, the opposite is true for amino acids. That is, most amino acids found in nature have the L configuration, with the amino group pointing here to the left in the Fisher projection. You should also remember from Chapter 22 that there is no direct way to correlate L or D with R or S. The only thing that we can say is that if an L amino acid happens to be S, then its D isomer will be R, and vice versa. And just in case any of you appear in a trivia show later in life, you might want to know that all of the 19 l-amino acids that have stereocenters, glycine does not have a stereocenter, so it's not included. But those that do have stereocenters happen to have an S configuration, except for cysteine, which has an R configuration. If any of you guys want to know why, you can ask me in class. The author of our textbook claims that the easiest way to remember these 20 amino acid structures is to separate them into individual categories according to their properties. That might be true for some people and might be incorrect for others. I suppose that depends on the way that you personally happen to memorize things most easily. For me, I find that the easiest way for me to remember things is by creating my own vulgar limericks. Actually, I'm just kidding. I don't have one particular memorization technique that I use all the time for everything. But for me, I often happen to be able to remember concepts by making up my own crazy acronyms. For example, I can remember the name of all the amino acids that have nonpolar side chains, these ones shown on this slide, by remembering the acronym phrase, I lag at PP. Isoleucine, leucine, alanine, glycine, valine, methionine, phenylalanine, and proline. I lag at PP. Now, I understand this might sound borderline vulgar, but the fact is, vulgarity is usually really hard to forget. For remembering the amino acids with polar neutral side chains, those ones that are shown here, you might consider remembering the acronym phrase, thanks, that's yuck. Threonine, asparagine, tryptophan, serine, tyrosine, glutamine, and cysteine. For remembering the amino acids with polar acidic side chains, you might consider remembering the phrase, always good. Aspartic acid and glutamic acid. And for remembering the amino acids with polar basic side chains, I want you to remember the acronym HAL. He's one of my favorite characters from the show Malcolm in the Middle. Anyway, HAL stands for histidine, arginine, and lysine. Now, one thing I want to tell you with absolute invariable hesitation is that I am not going to quiz or test you on these acronyms. I really can't. They're just Mike's own dorky way of remembering the amino acids' names. You can come up with your own way of memorizing their structures and names if you wish. Also, I'm not going to require you in this class to even memorize the amino acids' names and structures. That will wait for our biochemistry class, which will happen in a later semester. Nevertheless, I do want you to at least have some exposure to their structures and names. And if my acronyms and phrases happen to help you, so be it. If not, then please forget them. Now to something else. You should know that amino acids can never exist as uncharged compounds. That is, you'll never see an amino acid existing in a neutral state. like the one shown right here. Why? Because a carboxylic acid is way more acidic than an NH3+. In other words, this hydrogen right here is way more acidic than these hydrogens right here. So if you wanted to have an amino acid exist in its neutral form that I've X'd out over here to the left, in order to get that, one of these hydrogens would have to be removed before this hydrogen was removed. And that's never ever going to happen, because these hydrogens over here on the nitrogen are way, way less acidic than the hydrogen over here. Hence, once again, amino acids will never exist in this neutral state. I just have to tell you that because that might come across as being a little frustrating for you when you continually see us abbreviating them with having charges here, either in one position or the other or both. So yeah, I just want you guys to know that. Now, because of this fact, at neutral pH, around pH 7, amino acids look like the picture shown right here. Now, just so you know, compounds like this one, which have a negative charge on one atom and a positive charge on another atom, are called zwitterions. Now, this word derives from a German term, Zwitter, which means hybrid or hermaphrodite. You know, I've got to tell you, I think I really don't use the word hermaphrodite frequently enough in my everyday speech. Now, as we decrease pH in a solution, we increase that solution's acidity, which means that we're increasing the number of H+ or proton atoms in the solution. Hence, as pH goes down, the number of H+ atoms in the solution goes up, and we start to see things get more and more protonated. I'm going to say that again. As we get more acidic, pH goes down, which means that the number of H+ atoms goes up. So we'll see our molecules in acidic solutions get more and more H's stuck onto them. Does that make sense? I hope that it makes sense. So because of this, at low pH, amino acids will look like this. So I'm here at very, very low pH, lots of H+ lying around. I protonate everything, so I will protonate this O-, and I'll leave my NH3+ protonated. This is what amino acids look like at low, low pH. Now at high pH, we see the opposite trend happen. That is, at high pH, we see fewer and fewer H+ atoms and more hydroxide, OH- atoms or OH- equivalents in solution. Hence, as we increase pH, we start to see things get deprotonated more and more and more. So once again, as we increase pH, we decrease the amount of H+. We start to see hydrogens get removed from molecules. Hence, at high pH, amino acids will look like this. You can see that we've left our O- deprotonated, and now we've also deprotonated the NH3+ to leave it as a neutral NH2. I hope you can look at that, and I hope that doesn't blow your minds. You're welcome to pause this and replay what I just said until it really solidifies in your brains. It took me a while to actually grasp, I think, this concept here. Now, you should be aware of the fact that some amino acids have acidic or basic groups in their side chains, too. One example is histidine, which exists in various forms depending on the solution that it's in. So let's look here. If we start to get down to really, really acidic pH, pH 0, we have lots and lots of H+ around, so we're going to see more and more things get more and more protonated. So we see my oxygen protonated, my NH3+ is protonated, and we see this ring get protonated on the side chain as well. At pH 4, we're now less acidic, which means this OH is now deprotonated. There's not enough H+ around to protonate this O-. At higher pH, we now see this ring here get deprotonated, and then at the highest pH, we see everything deprotonated. So once again, there are some amino acids that have groups that can be protonated or deprotonated on their side chains. Those kinds of amino acids are amino acids that we say have ionizable side chains. Now here's a table showing the 20 most common amino acids with their pKa values shown for their carboxylic acid and amine groups. So if we look here at this table, we see the 20 amino acids. We look here, we see the pKa values of their carboxylic acid groups for each of these, and of their amine groups for each of these. For amino acids that have ionizable side chains, those are arginine, aspartic acid, cysteine, glutamic acid, histidine, lysine, and tyrosine. The pKa values of their side chains are also shown. And this brings us finally to our first lecture problem. I want you to draw the predominant form of each of the following amino acids at pH 7.3. As you're probably anticipating, I'm going to give you the answers to a few of these examples over the next couple of slides. If you want to try them before looking at my instruction, go right ahead. If not, we can barrel right through this. So now I'll talk you through the steps involved in answering this kind of question. Remember, the question is, draw the structure in its form that it would exist at pH 7.3. The first structure on this list, was aspartate. So here's step one. We draw the molecule fully protonated. That is, with all its carboxylic acid groups as OHs and its amine groups as NH3 pluses. So here's what aspartic acid or aspartate looks like. Now remember, aspartic acid has an OH in its side chain too, and an OH in its carboxylic acid group that all the other amino acids have, and an NH3 plus. So this is step one. We draw it fully protonated. Step two, from the table that we showed on the previous slide, we write down the pKa values for every OH and NH3 plus group. Here they are. You're welcome to double check them, make sure I'm not lying. Step 3. We now redraw the structure, deprotonating every pKa that's below the pH, which is 7.3 in this case, and leaving protonated every pKa that's above the pH. So let's take a look at this. At 7.3, we kind of look at this. We ask, is 2.09 below 7.3? It is. So that means we're going to deprotonate this. Is 9.82 below 7.3? It is not. So we're going to leave this protonated. Is 3.86 below 7.3? It is, which means we're going to deprotonate the side chain. So here is what aspartic acid will look like at pH 7.3. Let's do our next example, and I'll remind you of these steps. Step 1, draw everything protonated. And our example here is histidine. So histidine has this ionizable side chain here where we can protonate one of the nitrogens here. We leave the OH protonated and the NH3 plus protonated. Then we go to step 2. Write the pKa value for every single group, which we've taken from the table shown previously. Here they are. Step 3. Redraw the structure, deprotonating every pKa that's below the pH, and leaving protonated every pKa that's above the pH. Let's take a look. At pH 7.3, we ask ourselves, is 1.82 below 7.3? The answer is yes, so we deprotonate this. Is 9.17 below 7.3? No, so we leave it protonated. Is 6.04 below 7.3? Yes, which means that we deprotonate it. So what does that mean? It means that histidine will look like this at pH 7.3. Now, that is the answer to those first two examples. I'll leave it up to you to try and answer the question for the remaining amino acids that I listed in the question on slide 18. For that, I think it's a great place for us to conclude today's exciting presentation. But don't worry, there will be more. So please stay tuned for my next exciting installment on amino acid chemistry.